Forest disturbances such as hurricanes play a key role in shaping the future species and state of the environment. Point Pleasant Park in Halifax experienced such disturbance when Hurricane Juan struck in 2003. The hurricane destroyed approximately 75% of the trees, resetting proportions of the forest. In light of this, the opportunity presented itself to collect data displaying succession of an environment in real time as the forest of Point Pleasant Park healed. Data is being collected every year following the hurricane by Dalhousie students. Forest community, dominant species density, and other community metrics were analyzed to understand more thoroughly how succession occurred in this area. The preservation of this park is also very important to the Mi'kmaq Nation because it allows them to feel close to nature even while living in a big city like Halifax, which is an important part of their culture and their spirituality. Our objectives are to analyze the changes in the forest community in Point Pleasant Park and how it will progress and change over time. Also to analyze the change in densities of dominant species in Point Pleasant Park and understand how certain species not just thrive but dominate and why. And to analyze the changes over time of species richness in Point Pleasant Park as it moves towards its climax community after Hurricane Juan. Our hypotheses for this are the forest community will increase in shade-tolerant species and ground flora will decrease. Red spruce and red maple densities will continue increasing and dominating toward the climax community due to their shade tolerance and longevity. Overall species richness will increase moderately over time and as the forest moves towards its climax community.
We collected data on flora within Pleasant Point Park in 1 out of 6 designated areas, all 20 meters by 20 meters in size. These sites were chosen because they were the areas where the hurricane impacted forest structure the most. In each site, 2 major variables were measured by us: trees and ground flora. All trees within the site were measured, so long as they were greater than or equal to 2.5 centimeters in diameter at breast height. A flexible measuring tape, also sometimes called the Taylor's tape, was used to measure the diameter at breast height, with the measurement taken at approximately 4.5 feet or 1.3 meters. The percent coverage of ground flora was measured using 1 meter squared wooden squares called quadrats. An object was first tossed from the edge of the forest plot over the shoulder randomly, landing somewhere in the site. Wherever that object landed became the center of where our first quadrat was placed. Once all of the species in that quadrat were first identified and then had their percent coverage estimated, an object was thrown again from where that most recent sample was taken. This was repeated 12 times per site and was done this way to ensure that the data taken was random, variable, and unbiased.
The forest in Point Pleasant Park is changing as the shade-tolerant and slower-growing species, such as the red spruce tree and red maple trees, will progress and slowly replace the species that are successful early on and are very light demanding. Since there will be an increase in tree density, less flora will be able to grow on the ground because of the decrease in the amount of light that the forest would get. We predict that the forest community will grow and populations will stabilize as time goes on, and that the shade-tolerant species, such as the red spruce and red maple trees, will become the dominating species in the future.
This experiment was performed to observe how the density of dominant species in Point Pleasant Park has changed over time, specifically from the year 2004 to 2025. All tree species in the 6 specific sites were identified and had their diameters measured. Figures 2 and 3 show how the number of spruce or maple individuals per 20 meter by 20 meter plot changed over time. And as you can see, there were significant increases in density over time shown in both species. Red spruce density increased slightly each year, but significantly over time, When looking at the regression equation, we can see an increase of 0.35 trees per plot per year. This shows us that spruce abundance did rise from 2004 to 2025. However, when we look at the R2 variable, we see that time explained only 13% of the increase in density. Now, on the other hand, red maple density increased significantly over the study period, around 2.24 trees per plot per year, showing a steady rise in red maple abundance from 2004 to 2025. Although maple density increased more than spruce, time explained only 14% of that increase in density, similar to the spruce. As stated, from 2004 to 2025, both tree species showed an increase in density. The positive slopes in both regression equations show that both species have become more abundant in the 21 years they have been sampled. The larger slope of the red maple data shows us a faster increase in maple density than spruce. Although both species densities increased year to year, the R-squared value shows that time as a factor only explains 13 to 14% of the increase in density. This means there are many other potential factors that are influencing this. These factors could be temperature, soil pH, nutrients, water, or light availability. The increase in red maple and red spruce density can be explained by classic successional processes following a major disturbance like that of the hurricane. Similar to how pioneer species colonize new ground after something like glacial retreat, the hurricane destroyed and toppled many tall trees, leaving lots of open gaps in the canopy of the forest. This gave way to greater resource availability. With less trees, there was an abundance of light, exposed mineral soil, and less competition for nutrients. All of these variables were favorable to red spruce and red maple. These two species are quite shade tolerant, but mature very quickly in the juvenile stages of their lives if they have access to lots of light. Similar to how pioneer species modify their environment to suit later species, the disturbance of the hurricane allowed these dominant trees to reestablish themselves under less canopy competition, which in turn led to increased density. Now that we have established what has happened, I would like to predict what could happen as time progresses. We can predict that red maple and red spruce densities will increase as the forest approaches its climax community. However, the species densities between the two will progress at different rates. Because maple and spruce are long-lived and shade-tolerant species, it's likely that they're going to outcompete other colonizers. Maple and spruce are going to increasingly dominate as the canopy closes. Red spruce is the more shade-tolerant and longer-lived of the two and will probably become more dominant in the upper canopy as maple becomes more dominant in the middle to lower canopy. The densities of shorter, light necessary species will likely decline, while the late successional species like maple and spruce are going to persist. Therefore, as the forest moves towards its climax community, a stable and late successional stage, longer-lived and shade-tolerant species, like those of the red spruce and red maple, will dominate the forest.
Here we have a linear regression graph showing the change in species richness over time in years. We can see that in the beginning there was a very low amount of species richness, about 2 to 4 species per 400 meters squared area, but as time goes on, we start to see a moderate linear increase in species richness, up to as high as 15 species per 400 meters squared area as the forest matures. According to the linear regression, the species richness has increased at a rate of about 0.5 species per year, as previously shown in the linear regression equation. We can predict that the species richness will continue to increase slowly as the forest moves towards its climax community due to the statistically significant positive linear relationship between species richness and time. This trend was also apparent in a study done by Shi et al. In 2008, which analyzed changes in forest structure, species diversity, and spatial patterns in the Piedmont, North Carolina forest after Hurricane Fran in 1996. In terms of species diversity, they found that there was a slight increase in non-native tree species and shrubs in the forest 5 years after the hurricane, and no native species were lost. As the forest in Point Pleasant Park reaches its climax community in the later stage of succession, we may predict that there will be a higher species richness, as this is what Shi et al. Found in their 2008 study when the Piedmont forest moved towards its climax community of uneven-aged hardwoods. In conclusion, after analyzing the data from the Acadian forest at Point Pleasant Park, we find that it is likely in a mid to late secondary successional stage. Patterns suggest that the forest is recovering from the disturbance caused by Hurricane Juan. We suggest that trail maintenance and recreational use can limit natural regeneration, but tree planting programs could promote the growth of certain species, accelerating the rate of succession. Two-eyed seeing is a concept that was introduced into integrative science by Mi'kmaq elder Albert Marshall in 2004 that incorporates the best ideas from both Western and traditional indigenous knowledge. This way of thinking takes perspectives of economics, environmental science, and social science and focuses on principles of coexistence, interrelatedness, interconnectedness, and community. Using two-eyed seeing can help us to restore the mature Acadian forest in Point Pleasant Park because the indigenous peoples have been connected to this land for generations, and their traditional knowledge passed on from generation to generation will give us more insight that could not have been common knowledge in Western science.
As we end this presentation, we wanted to acknowledge Dr. Joanna Zagoras for facilitating this lab exercise. It was a great, very good experience. Also, I wanted to acknowledge Dalhousie for providing our research tools and resources. And lastly, past Biology 2060 students and surveyors that took the Point Pleasant Park forest data over the years.